turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the programme where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith, and with Sally LePage.
This week, as COVID cases take off again in Europe, we review the situation here in the UK. Also, making strawberry smells with mushrooms and breakthrough textiles that cool you down when the sun shines on them.
Plus, as we strive for a more sustainable future, we're asking, would be good to help us build everything from better buildings to knives and even biodegradable glitter.
The Naked Scientists podcast is powered by ukfast.co.uk.
But first, COVID cases across the European continent are surging to the extent that some countries are resorting again to drastic measures to control outbreaks. The Netherlands has imposed new lockdown restrictions. In Ireland, curfews on pubs, clubs and restaurants have been reintroduced. And in Austria, COVID vaccines will be made mandatory.
So how are we faring here in the UK? And should we be following suit? Or should we hold our nerve? David Matthews is a virologist at the University of Bristol, and he's in the latter camp.
Currently, I think we're in a good place. I'm very optimistic. We have a highly vaccinated population. Coupled with that, we've had quite a lot of spread, which acts as a boost to people who are vaccinated. And then, of course, we've got the booster program, which will boost the immunity of people who've not been infected but have been vaccinated. So I am optimistic. We're starting to see a decline in cases and deaths slowly. So I do think we are hopefully turning the corner.
Well, I share that optimism, but I'm slightly confused by the headlines that we're being assailed by, because if you look at the vaccine uptake rate, we're at nearly 90% of the population over 12 have had at least one dose of vaccine now. So have we really got much ground to gain still by continuing to push on the vaccine front? Do you think that 10% are actually going to go across the line here?
I don't think they're going to go across the line without a lot of help from everybody else. I don't know why that 10% are resisting, but I think we need to spend a lot more time working on that problem and persuading those people of the benefits of the vaccination and helping them to understand or maybe backtrack from earlier positions they've taken and now feel slightly awkward about changing their minds. We need to work on that, because if we were to do that, you would basically halve the number of people in hospital and on mechanical ventilation beds in a single go if everybody in the adult population was vaccinated.
Is that the statistic then, that half of the cases we're seeing needing the most help in hospital at the moment are unvaccinated?
Almost. So I think the last time I checked, it was something like 2/3 of people on mechanical ventilation beds and needing additional help in hospital are unvaccinated. If you're vaccinated, that reduces the chance of you ending up in that situation by about 80-90%. So, a very rough top of your head calculation tells you that effectively leads to a halving of the numbers. So we'd go from 1,000 people a day on mechanical ventilation beds as we are right now to 500. And that would obviously mean that we'd be much, much further away from the prospect of lockdown.
What's your take on the fact that Northern Ireland, they're moving towards, in all likelihood, introducing some kind of vaccine passport system? Is this vaccine passport system actually worth pursuing?
Well, I think a vaccine passport, if it helps to persuade people to get the vaccine, then it's a good thing. We are obviously in uncharted territories. I would rather we persuade people rather than compel them, but I do see the merits in compelling people. I really do. The numbers, as we said earlier, they speak for themselves. 2/3 of people in hospital in serious conditions right now were unvaccinated. And the NHS, as we know, has much, much better things to do with its time than spend time treating people who turn down a free, safe and effective vaccine.
But that does mean that we're potentially foisting additional burdens on 90% of the population, whereas only 10% are the people who actually are the cause of all that.
Yeah, absolutely. And that's why it's a frustration. I think if we were going to introduce vaccine passports, for myself, if I was making these decisions, I would have made the decision to do that before the summer while we were still in lockdowns, so that people got used to the idea of some freedoms, but some restrictions still, rather than letting everybody go out and enjoy their freedom and then start to put restrictions back on. I think we have missed the greatest window of opportunity by not having a vaccine passport plan at the very beginning of the summer. I'd rather we had a strong and concerted campaign of persuasion, talking to people who are vaccine hesitant to try and understand their fears, allay their fears, and show them that they really should change their mind now and get jabbed.
Do you think that we're actually probably at the point where we should begin to say to people, we need to get our confidence back and get back on our horses? Because actually, if one compares what would happen with the flu around this time of year and going into winter and the mortality costs, the NHS impact, we're not far removed now we've got COVID vaccines from what the flu does to us, are we?
We're not very far removed. And I think that alludes to another point, which I think people are not really thinking about much and not thinking through properly, which is this, that everybody on this planet, all 7 billion of us, will have their day with this virus one day or another. Be it this winter or next winter or the winter after that. There's no dodging this virus now. You will meet it. The only question is, do you want your immune system to meet this new virus, trained or untrained for the encounter? And if you need to meet it trained and ready for the fight, then you need to get vaccinated. This is a permanent addition now to the smorgasbord of respiratory diseases. I think with vaccinations and exposures over time, it will become another common cold and not a dangerous disease as it is right now. But yeah, I think we're approaching the point where it will be like flu or respiratory syncytial virus, or actually possibly even milder than that, and just like the other human coronaviruses.
Let's hope so. David Matthews there. Now, scientists are gearing up to swap skilled chemists for fungi in a lab in Germany. Well, not quite, but they have stumbled on a strain of fungus that, when grown on certain forms of plant waste, can break down the waste into a suite of chemicals that smell just like wild strawberries. The rationale for this work is that whilst shop-bought strawberries taste great, many people think that wild strawberries taste even better because they have a stronger, more floral aroma. But sadly, wild strawberries are so small that it's not viable to extract useful amounts of their flavour compounds from the fruits themselves. Instead, this means we have to rely on artificial flavours, and this comes at a cost both financially and for the environment. But fungi, of course, work for nothing. I spoke with Holger Zorn from the University of Gießen to find out more.
Mushrooms are living in the completely different environments. So they have the enzymes to break down almost each and every organic material. And that gives them the opportunity also to modify substances that are already present in the starting material to release pleasant or sometimes also unpleasant flavor compounds.
So how did you test which fungi make the best smells?
We grew the fungi just on a plate on pomace of blackcurrant, and we just smelled every day to see if a pleasant flavor developed or not.
So you're growing these fungi on this blackcurrant pulp. Where does that come from?
That is coming from the juice processing industry, just from blackcurrant juice production.
And why are you using that of all the things you could be growing your fungi on?
It's a quite sustainable approach. This material is typically just discarded. And of course, we know that a number of potential potent flavor precursors are still present in the material. So in general, though it is currently discarded, it's a valuable material, and we just want to make use of that.
So you're adding this library of fungi to this blackcurrant pulp. How did you work out which ones smell of wild strawberries? Is it just a matter of smelling them, or is it a bit more high tech than that?
The first step, of course, is just smelling. Our nose is by far the best instrument we have with us if we are talking about flavor compounds. And what we also have in our institute, we have a couple of well-experienced PhD students and postdocs that in a panel evaluate the flavors. And in this case, with this fungus, all of them agreed that it's highly interesting, and all of them said, oh, that's just like wild strawberry. Of course, in the next step, we use highly sophisticated analytical techniques, including gas chromatography and also sniffing gas chromatography, which means that we have a human nose as a human detector coupled to a chemical machine.
You say a human nose. This is attached to a human, so you have a person attached to the machine.
Yes, it's not detached from the human. person is still behind the nose, yeah.
I just love the idea that the best way of detecting these compounds is still just to sniff them. I'm sure that in chemistry at school I was told not to go around sniffing random things in the lab.
Yeah, that's different in food chemistry. Of course, we each and every time use our nose to detect interesting things in nature.
So you didn't set out to look for a wild strawberry smell. You were just like, let's put these fungi on this blackcurrant waste byproduct and see what happens. And it just so happened that one of them was wild strawberries.
Exactly, that's just what happened. We didn't deliberately search like a wild strawberry flavor. That's just what came out.
Was it more than one fungus that made this smell, or was it just the one particular one that happens to smell like strawberries?
We had several fungi that produced interesting and pleasant flavors, but this one, this Wolfiporia coccus, was the only one that produced this wild strawberry type flavor.
And what does that fungus look like? What does it do in the wild?
In the wild, it lives at trees, and it looks a bit like a coconut.
Does this coconut fungus smell like strawberries in the wild when it's growing on wood?
Not at all. It only smells like strawberry when you grow it on this blackcurrant pomace.
And what are the benefits of making flavours using fungi over the traditional chemical routes?
One benefit is that these types of flavors may be labeled as natural flavor compounds, as they are, of course, made by nature. So it makes sense to label them as natural. And the second aspect, the production of these bioflavors is much more sustainable than traditional chemical synthesis.
Well, I'm sure there is mushroom in the market for a wonderful discovery like that. Holger Zorn there.
From baffling British weather
sideways spines of the vertebrae coming off here
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Now, still to come in this hour, how scientists have used nanotechnology to produce silk shirts that will cool you down when the sun shines, and we visit one of the tallest buildings made from wood in the UK.
When you think of a newborn baby, I bet you associate it with their smell. A family legend is that I was, as a baby, handed over to the actor Ben Kingsley because he loved the smell of newborn babies so much he wanted to sniff my head. I mean, it's certainly a distinguishing smell. But although we don't think of humans as being particularly sensitive to smell, maybe smell is more important than we give it credit for. Noam Sobel and Eva Mishaw from the Weizmann Institute of Science in Israel certainly think smell is nothing to be sniffed at.
There's a term from German zoology, Umwelt. Umwelt refers to the primary perceptual world an animal lives in, right? So granted, humans' Umwelt is visual and then auditory. Now, that, of course, is not true for many other mammals, right? I mean, if you would ask your dog or your cat, they would certainly give up vision and audition before they would give up olfaction. So animals differ in that way. And yet, for humans, even though it's not the primary sensory aspect we use to perceive the world, it's still super, super important that, our nose guides very, very important decisions in our lives.
Does it affect then the way in which we socialize as well?
For sure. We were contacted by colleagues from Germany who study chemosignaling not in humans, but in mice. And that is the communication using chemicals, using body odors. We study this quite extensively, and they identified a specific molecule, hexadecanal, and we'll call it hex from here on just for convenience. So they identified hex as a molecule that's emitted primarily in the feces of mice and has social influence in mouse behavior. Where put in simple terms, it makes mice chill. Now, Breer and Stutzman went on to identify the very specific olfactory receptor that responds to hex. And moreover, they then observed that this particular receptor is highly conserved evolutionarily. That is, that you see it or its homologs in lots and lots of mammals, including humans. So they actually sent us a bottle of the stuff by mail and said, hey, we think it's going to do something in humans. because it does this and this in mice, and we think this is highly conserved across mammals.
And thank goodness they did. How does one either go about testing using this hex that's arrived in the post to see how aggression changes?
So aggression is a social behavior. We brought participants to the lab. We had to make them frustrated.
I think we made people angry more than we made them frustrated.
And how do you two, I imagine you're very good at this now, but how do you two make people angry?
We asked them to reach cooperation with someone else, which was in fact a computer algorithm, not a very nice computer algorithm. So here we told them, now it's a completely different task. This task is a time reaction task. Just press as fast as you can. But then if you press faster than this other participant, you get to noise blast them. So we just provided an outlet.
I've got a little clip of the sound, actually, so let me play it for you at home. It's a pretty grating sound, isn't it?
Yes. I've heard it many times.
And what do you find?
So when men were exposed to hex, it was a small effect, but incredibly consistent. They used noise blasts that are lower in their volume, like less severe noise blasts. But to women, when we're exposed to hex, they used more severe noise blasts.
Why is it that hex has this effect? Do we have any idea?
Typically in the animal kingdom, definitely in the mammalian kingdom, and sadly also in humans, paternal aggression and male aggression is often sadly directed at offspring. By contrast, maternal aggression is typically protective. So if you're an offspring, you have a vested interest in making your mother more aggressive and in making your father less aggressive.
An interesting hypothesis, you know, the smellier your baby, the more aggressive the mum and the more chilled out the dad.
The final icing on the cake here that I should add, we went to a paper that was published just a few years ago by a group out of Japan. So this was really cool because it was hypothesis driven. We came to them and said, look, you know, we're expecting to find hex here. And lo and behold, hex was the most abundant semi-volatile they found in heads of babies. So this came from full circle, right? Because not only do we hypothesize it should be there, but it in fact is there at very high levels.
Eva Mishaw and before her, Noam Sobel. They're at the Weizmann Institute. They were talking with Harry Lewis, and that work came out in Science Advances.
Now, remember that bit in Back to the Future where Marty McFly gets soaked, but his special self-drying jacket kicks in and saves the day? Well, we're not quite there yet, but scientists have now successfully used nanotechnology to produce a form of silk that gives you, in their words, wearable air conditioning. Exposed to direct sunlight, it actually keeps your body cooler than the surroundings by using nanoparticles glued onto the strands of silk to bat away ultraviolet rays that would normally heat up the material and the wearer. By radiating your and the shirt's heat off into space, it cleverly means you're cooler than the surrounding air, and not just because you look good. Stanford University's Shan Hoi Fan told Jacopo Russo how it works.
What we have demonstrated is that nanoprocessed silk, when placed under direct sunlight by itself, can reach a temperature that's 3.5 degrees Celsius below ambient. And therefore, a person wearing such a nanoprocessed silk in an outdoor setting is essentially wearing its own air conditioning.
So how did you treat the silk?
Native silk absorbs ultraviolet light. Absorption of ultraviolet light gives rise to heating of the textile. We introduced aluminum oxide nanoparticles into the silk. Nanoparticles just look like a little ball, except they are very, very small. The nanoparticle that we put in is designed so that it reflects strongly the ultraviolet light.
How did the nanoparticles stick to the silk?
We put a chemical bonding agent to ensure that the particle connect to the protein in the silk in a strong way.
So they're not just going to be washed away after a cycle in the washing machine?
In fact, we did many cycles in the washing machine and confirmed that the particles are still there after many washing cycles.
Okay, that's good. So now we've got our engineered silk. How did you measure its cooling properties?
We do two measurements. In the first measurement, we simply take a silk, put it under the sun, and measure its temperature. In that case, we see a temperature that's about 3.5 degrees Celsius below the ambient air temperature. The next thing that we did, which is to try to simulate the silk when a person is wearing it, is that we place this on top of a artificial skin with a heat source to simulate the thermal property of human body and put it outside under the sun. And what we see is that the nano-processed silk has a temperature that's about 8 degrees Celsius below that of the native silk.
Right, and just to clarify, if you put a piece of silk or cotton out in the sun, it will usually be hotter than the air around it, right?
Yes, and in our nano-processed silk, its temperature actually is colder than the environment.
Amazing. And are there no other wearable materials that can currently do that?
No, so this really is quite an unusual textile that we have created.
Could this process be scaled to make T-shirts?
I believe so. In fact, we have a picture of a shirt made out of the silk. You certainly can make that kind of scale.
I guess this means if I wear this T-shirt next summer, I won't have to use the air conditioning as much. So I will save energy, essentially.
That's right. But also in an outdoor situation where air conditioning may not be readily available, you will actually feel cooler.
Amazing stuff. Shan Hui Fan, and that research was published in Nature Nanotechnology. When world leaders gathered in Glasgow for COP26, the climate change summit at the start of the month, something that got some of the delegates into hot water, if not hot air, was how many of them got there. Most of them came by air. And of course, flying releases significant amounts of greenhouse gases, which is why we're repeatedly being reminded that cheap flights actually cost the Earth, and we should try to minimise them. But rather than going cold turkey and cutting our flying dramatically, Milan Kluwer from the University of Oxford has found that with just small reductions in flights each year, we can neutralise aviation warming effects.
Ladies and gentlemen, may I have your attention please as we go through the following safety instructions. Make sure all seats are in the upright position and trays are put away before we take off.
For many people, flying is the biggest contribution to global warming. COVID really forced us to rethink how important is it to fly. Suddenly, 10 days quarantine for everyone, right? People really thought about whether it was worth it. And in our study, we find that an annual decrease of 2.5% in terms of flights would limit aviation's contribution to global warming with an immediate effect. It's a bit tricky to understand why this is, because usually we think in terms of carbon emissions, and carbon emissions mean that the more we emit, the more increases the warming. However, because of the non-CO2 effects that aviation contributes, aircraft engines at the altitude at which they fly, they also emit nitrogen oxides. Nitrogen oxides then start triggering chemical reactions. So one thing they, for example, do is they decrease the amount of methane that actually has a tiny cooling effect. They also interfere with the ozone that net has a warming effect. And one of the major ones is the creation of these condensation trails that we can see. They can basically form cirrus clouds, and these cirrus clouds then act as a net warming. If you take all of these effects that are not the carbon dioxide emissions together, we usually call them non-CO2 effects. They increase the warming that is caused by CO2 alone by a factor of 2. These effects decrease over time, meaning that actually if you fly less than in the year before, this effect slowly decreases and balance the increasing CO2 emissions. At this rate that we've calculated, the minus 2.5% per year, we actually find that there's this balance of the CO2 and the non-CO2 effects is such that there's no further warming introduced.
Does that mean we would have to stop flying completely?
No, and this is exactly the point that we want to raise. The only thing that we need right now is a change of direction. If we get a change of direction, so we slowly decrease, then the additional warming that is caused by aviation is halted. And I think this is a very important message.
Could you describe your method?
Basically, we connected the whole dots between knowing what the fuel consumption is in a given year, down all the line to what is the temperature increase that is caused by these emissions. And because we've connected all these dots, we can now also assume for the future a given consumption of this jet fuel, and we can see what will happen if it increases, if it decreases.
Could we theoretically achieve the same reductions in emissions through technological advances?
At the moment, it is not possible because we do not have alternative low carbon fuels available at the moment. The production of these sustainable aviation fuels, even if they were sustainable, is currently not available at scale that is needed. So before the pandemic, annually, every day, 1 billion liters of jet fuel was burned. Of course, people also talk about electric airplanes, but at the moment, the batteries are just too heavy. And even in the next decades, if something like that would be available, it's only very short haul flights.
You mentioned this 2.5% reduction in flying per year. What would this look like for the average person in one of the richer countries?
At the moment, actually, it wouldn't change that much because the global levels of air traffic during COVID decreased about by a factor of 2. What I often hear is these messages say, like, in the future, I'll try to fly half as much as I did before. What physically is needed is a reduction of 2.5%, which is obviously much less. Technically, what we need, general awareness that we have to distinguish between necessary and unnecessary flights. Everyone has to ask themselves this question: is it really important that I fly, or can I replace this flight? Can I combine several journeys into a single one? The only thing that we really have to change is this idea that the whole aviation sector should grow and grow and grow.
So a little goes a long way. Milan Kluwer there. That study was published in Environmental Research Letters.
Much has changed for business owners, managers, and staff recently. But with over 30 years' experience in telecommunications, award-winning independent company Spitfire have the expertise to make sure you stay ahead and can keep on innovating. Whether it's connectivity, MPLS networks, firewalls, or phone systems, Spitfire can help. To find out more, go to spitfire.co.uk. That's spitfire.co.uk. Spitfire, telecoms and IP engineering solutions for business since 1988.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
But right now, you're with your favourite science show, and that's The Naked Scientists with me, Sally LePage. And for the rest of the show, we're talking all about wonderful wood. And with me is University of Cambridge materials engineer Jacopo Russo, who has been working with us at The Naked Scientists. So, Jacopo, why are you so interested in wood?
I'm interested in wood because it's a natural material. And although we often associate it with old building techniques, actually has a lot of potential to be a sustainable solution for our future.
Interesting. Well, before we go on to some of these sustainable futuristic techniques, let's go back to the basics. What exactly is wood?
Well, I ventured out of the office this week for a walk in the woods to find out just that. When I'm deep into a project and I can't see the wood for the trees, I like to go for a walk to clear my head. The Naked Scientist office is based in Madingley, just outside Cambridge, and we're lucky enough to have a patch of woodland just across the road. It's a crisp autumnal day. There's leaves everywhere on the ground, and I'm surrounded by trees, which, as we all know, are made of wood. Of course, we're familiar with it, but what exactly is wood? Well, it's made of 3 main parts: cellulose, lignin, and hemicellulose. Cellulose is a chemical made out of sugar molecules and makes fibers that are very strong in tension. These fibers are like chains, which means if you pull on them, they will resist. But if you try to squash them, they will crumple. This would be very bad news for the tree, so to prevent it, trees strengthen their wood with lignin, a stiff polymer with a messy structure that stops the cellulose chains from collapsing under their own weight. Lignin is also what gives wood its brown color. Finally, to stick the two together, there's hemicellulose, which gives wood flexibility. To the right of me here, there's a beech tree, with its lovely red and yellow leaves. And to the left is a spruce, which will hold to its needle-like leaves all winter long. Deciduous trees, like beech, produce what we call hardwood, whereas coniferous trees, like spruce, make softwoods. These two groups of trees have been evolving separately for hundreds of millions of years, so their woods have very different structures, with hardwoods being a lot more complex. However, just to confuse things, not all hardwoods are hard and not all softwoods are soft. Balsa wood, which is a very soft wood used to make model airplanes, is technically a hardwood, whereas yew trees, which you often see in graveyards, give a very hard wood, but are categorized as softwoods. Ahead of me I see a tree that's been cut down, with the characteristic rings that give wooden furniture the beautiful grain with dark and light lines. This is all to do with the amount of lignin, which you may remember was the brown bit in wood, and is found on the outside of the wood cells. In spring and summer, trees grow fast, and the cells are large to allow nutrients to travel from the roots to the canopy. This means there's less space for lignin. In autumn and winter, trees grow more slowly. Being strong and standing up to harsh weather is more important to them, so a lot of lignin is produced, which explains the darker color. What I've always found baffling about wood is that it may look sturdy, but actually at least half of a tree is made from the air. Thanks to photosynthesis, trees transform carbon dioxide from the atmosphere into the sugars that become the wood. And get this, to grow 1 kilogram of wood, a tree has to draw down 1.6 kilograms of CO2. That's why everyone talks about trees as one of the main solutions to oppose climate change. But we have other uses for trees beyond carbon sequestration. Of course, it's easy to think of houses made of timber and of wooden furniture, but in fact, in the US, half of the harvested timber is used in wood pulp and paper production, and even in places like Europe, a quarter is burned as fuel. I've got to get back to the office now, but it does make me think, are there better ways we could be using this marvelous material?
So that's where you've been going when you're nipping out of the office, eh, Jacopo? You've mentioned that we use timber in houses, and I've certainly noticed a trend towards using wood in more parts of the building, like the new mosque in Cambridge and the new library in Magdalen College all feature wood very strongly. Are wooden buildings becoming more popular again?
So, well, to build tall buildings like the skyscrapers you see in London, the materials we use by far the most are still concrete and steel. But more and more architects are now using this special form of wood called cross-laminated timber, or CLT, to make structures that are taller and taller. In fact, I went to visit Dave Lomax from Waugh Thistleton Architects to have a look at what is going to be the tallest office building made of timber in the whole of London. Right, so here we are. We're in Rivington Street, and I've just had the first sight of the black and white building.
Yeah. The basic principle of the building is that we're providing 6 floors of new office space in the middle of Rivington Street, a really tight little site with a railway on one side and small roads and all those sorts of things. And the principle here is that we've chosen to build the building in a way that is better for the environment. So instead of just doing the normal thing, going for a concrete frame and pouring lots and lots of grey stuff into the ground, we've elected to build it out of pieces of wood.
So the floors, I can see layers in the wooden planks forming the floor. What kind of wood is that?
So that particular material is one called LVL, and that stands for laminated veneer lumber. And what that is a whole series of hundreds and hundreds of veneers. Veneer meaning specifically that it was peeled from the tree rather than cut from the tree. And that product is incredibly strong. And the species that goes into that is beech. So those are hardwood elements. So that means they're much stronger. So with a really strong material like LVL made from beech, we can have much smaller columns, smaller beams, those sorts of things.
We've just entered the construction site. The first thing I notice as I enter the building is the smell. It's very nice, woody, and also construction smell, I guess.
Yeah, absolutely. I mean, the way I describe it to people is my dad's woodwork shop. Typically, this is a building made out of beams and columns. So that's very like a steel structure, slightly different to a usual concrete structure. So a concrete structure would normally have columns that just meet a flat slab. Now, the centre of the building deals with the horizontal movement. All buildings move horizontally with the load of the wind if they don't have something to stop them. So here, actually, what we use is CLT. CLT is quite thick. You can see them on the edge there. Average everyday chunks of spruce cut into planks and then laid in 5 layers, each layer at 90 degrees to the next. And that allows it to work a bit like the slab you would see in a concrete building. So it spans in 2 directions.
I suppose fire is one of the biggest concerns that people have with timber. Is this building going to be safe against fires?
All building materials suffer when there is a fire. When we have a piece of steel and we expose it to 300 degrees of temperature, it also is very likely very quickly to start to fail. But we do things to protect it from burning in a way that is dangerous to those fighting the fire or those being in the building at the time. So our approach to wood is pretty much the same. We know exactly how timber performs, how long it takes to degrade, so we know that this building can be on fire in certain places for a certain amount of time, which should be long enough for everybody to evacuate the building, and if they decide to do so, for the fire brigade to put it out.
How long is this building going to last?
Well, I mean, it's a really sensible question. I'm going to give you the politician's answer first. It comes with a warranty for 60 years. There's absolutely no reason wooden buildings can't last forever. We just need to look after them. So the principle with wood is, it's great if it gets wet and then dries out again. It's only when we start to trap water in certain places that we start to get problems, because then we get a cycle of kind of mould and fungus growing and rot and those sorts of things. All of this wood is really, really carefully treated in the way it's manufactured. It arrives to site at 14%, no more moisture content. That's monitored. And then we test it again before we put things like waterproof membranes on the roof so that we know we're not trapping water inside. But beyond that, belt and braces, you may even see some when we go downstairs. There are some little tiny holes in the roof.
So we got close to a square column here, and we're just going to touch it to see what kind of sound it makes. I was expecting it to be a lot more hollow as a sound. Instead, it's very solid.
Yeah, well, this material particularly, on the CLT panels, you can see they've maybe got 5 or sometimes 7, sometimes 3 thick layers in them. If you see the surface of this material here, I mean, we couldn't count them. There's probably 100 layers in that column that you can count right now. So what we've got is lots and lots and lots of layers, all packed tightly together through the surface of the column.
What's gluing the wood together, the wood planks?
It's not a particularly technically complex glue, but the difference is that all of these parts are pressed together in a really big mechanical press. So that's either a hydraulic press or it's a vacuum press, and that happens in the factory. So it's not just the performance of the glue, which needs to be one that can absorb into the lignin, into the cell structure of the timber. It also needs that kind of high pressure applied to it to give you the really strong adhesion we have. But the basic principle is sticky stuff and pressure.
So Dave, do you think then wood is a material for the 21st century?
I think it absolutely is. It's not the wood itself. The wood is no different. It's always been the same. But now these incredibly clever processes, working with a size and scale of material built to an incredibly tight tolerance in a factory in a way we couldn't have done even 40 years ago, that's why timber is the material of the future, because we're able to use it in such innovative and safe and clean and tidy ways.
That was Dave Lomax from War Thistleton Architects. Jacopo, it's really interesting that you mentioned the smell of the building site. What other kind of differences were there? Presumably the people who worked there were all woodworkers rather than your usual bricklayers.
Not really. I met someone called Jake. He was a construction worker that had worked on concrete and steel buildings before. What he was telling me is that the timber building construction site is a lot simpler and a lot tidier because everything is made in the factory and brought there already sort of ready to go up. So everything went really fast, and generally it's a better experience for people working on the site.
Interesting, because prefabricated houses have had an awfully bad rap in this country, particularly in the 60s and 70s, but it seems like they're coming back again.
Yeah, hopefully, in taller buildings and bigger structures maybe.
Surely it must take an awful lot of trees to build a whole skyscraper. Do you happen to know how many trees were in that building you went round?
I do. Dave told me. They used 1,800 trees from the Black Forest just for this one building.
1,800. Now, I know trees obviously absorb carbon dioxide, so is it sustainable to be cutting down that many trees to put in buildings? Shouldn't we be leaving some of them alive and in the forests?
Yeah, those are fair questions, which is why I put some of those concerns to Will Hawkins, a structural engineer at the University of Bath, who specializes in efficient and sustainable buildings.
When we're talking about replacing most concrete and steel structures with timber, most people would agree that using timber is better than the alternatives.
But we often hear that planting trees can help oppose climate change because trees absorb carbon from the atmosphere, and so they help offset the carbon we emit elsewhere. Can storing carbon in timber buildings also help oppose climate change?
I think the way to think about this is that the total benefit in terms of timber products can be thought of as the total amount of CO2 that's stored in both the forests and the products. So by making buildings and locking away CO2, you're increasing the store in timber products, but you have to make sure that by doing that, you're not just creating an equivalent reduction in the forests. So the key is to do this in a way that keeps the forest carbon storage high whilst creating new timber products and a new store alongside it.
Is it better to store timber in buildings for the environment?
It's better to use timber for products that are going to last a long time. So buildings have a really good advantage in that respect compared to something like fuel or packaging. We also need to consider what that timber is displacing. So for buildings, we'll be displacing steel and concrete, which we've already heard are quite highly emitting, but also we could be using that timber to replace fossil fuels, or we could be using it to replace, for example, plastic packaging. So it's not necessarily obvious. Timber is always doing good whenever we're using it by displacing something else. And it appears as though buildings is going to be one of the best ways that we can use it.
But at the same time, growing trees for that timber to store it in buildings requires land, and we already need land for many other things, like growing food. Is there going to be a problem with how we manage land in the future?
Our use of land is one of the key causes of biodiversity loss. And if we use it for anything else, then something has to go. And usually that's the natural world. So we always have to make a choice and make a compromise. And unfortunately, when it comes to timber, evidence shows that the more productive or the more timber is harvested from a forest, generally the lower its biodiversity tends to be. But timber plantations are often grown on less fertile soil, so upland areas. So there is scope to create new timber plantations in places that are not already that productive for agriculture.
I suppose one thing we need to worry about is what happens to timber buildings after they're demolished. What happens to the wood, to the timber usually?
So the majority of timber waste in the UK is actually burnt as biomass. So it goes into producing electricity. That offsets production from the grid, but also you're re-releasing that CO2 straight away. The rest is downcycled into either chipboard or MDF, or even animal bedding or compost. So again, we're going from timber structure, which can store biogenic carbon for a long time, into products that generally have a much shorter life. And that biogenic carbon is generally being re-released quite quickly.
So there seems to be a lot of different aspects to consider. What would you recommend we should do overall?
So I think our first priority is to just consume less. So we need to question whether we need new buildings at all. And we also need to reuse existing buildings as much as possible as a priority. Then if we decide that we do need a new building, the focus needs to be on material efficiency. So there's ways that we can create buildings that use a lot less material. So we can make the span shorter, or we can make clever shapes so that they're inherently strong and we don't need to use lots of material. And then finally, the last thing to do is to replace the concrete with the timber. But we really need to make sure that we're using only the smallest amount of timber that we can get away with, because those forests are already under pressure, and wherever timber is used, it does good.
That was Will Hawkins from the University of Bath. I'm still joined by materials engineer Jacopo Russo, and we're discussing the wonderful ways we can use wood. And still to come, we'll be learning about how you can make wood transparent and use it in windows instead of glass. But first, we now know we can build sustainable buildings from wood, but what else can we use wood for? Jacopo, are there any new technologies that are really transforming the wood?
Oh yeah, there are loads. Scientists are particularly interested in one ingredient of wood, cellulose, because at the nanoscale, this material has incredible properties, including bending the light in a way that gives rise to amazing colors.
Wait, so you take the cellulose out of the wood, and then for nanoparticles, so you grind it up into tiny pieces, and then what? It's just colourful?
Yeah, pretty much. The tiny pieces are called nanocrystals. And I went to visit Silvia Vignolini at Cambridge University's Department of Chemistry to see for myself how they're using nanocellulose to make glitter and pigments for cosmetics.
We are interested in cellulose because it's one of the two structural components together with lignin. And while lignin is a polymer that has a amorphous structure, the cellulose has a crystalline structure. And this crystallinity is what preserves as well the original fibrillar type of architecture that you have
In cellulose, all the molecules are arranged in a tidy structure. So when a light ray hits it, it gets manipulated in such a way that the cellulose appears colored to our eyes. Like when you look at the back of a CD-ROM, and if you tilt it at different angles, you see many different colors.
Structural coloration that we observe.
We're looking at a fume hood, and there's some liquid inside, and a magnet is rotating around to mix it. What am I looking at?
You are looking at one of the processes that we have to do during the extraction of this cellulose nanocrystal, because cellulose is something that you cannot synthesize, but you can only extract it from natural resources. We don't dissolve fully the structure of the cellulose, but we only remove this amorphous part until we get this nanocrystalline part.
So, by dissolving away the lignin in the wood, you're left with a suspension of cellulose nanocrystals floating around in water. I asked Silvia what they can use the suspension for.
It can be used directly as an ink for printing into printers. We can use it to make these large laminates of cellulose nanocrystal. We can use it to make other type of pigments. So this is our starting material for a lot of our experiments.
Are there samples that I can have a look at?
Yes, so we go to the optics lab, maybe.
So we've just interrupted an experiment. Everything was dark in the room, and I'm entering the optics lab. If you let the suspension dry onto a surface, you're left with a thin layer of nanocellulose crystals. And this is where the magic happens.
We have nanocrystals that are in suspension. And depending on the concentration of the suspension, the interaction changes. So if it's a really dilute suspension, they don't interact. As soon as you increase the concentration, so as soon as you force them to interact, reducing the volume of water, then you build up like a helical twist, and having this different orientation is what creates the color.
Okay, let's have When the water dries, the cellulose nanocrystals pack together. But the amazing thing is that they don't pack randomly. They spontaneously assemble to form a helix. Each nanofiber stacks on top of another at a slightly different angle. This tidy structure bends light in a way that gives color, as I got to see on a few samples in the lab.
I want to show you a beautiful one. This one is beautiful. Even if people cannot see it, but you can see, right, the difference.
So that's
it's
cool.
really metallic color, yes, and you think this is just cellulose, is the same.
So depending on the angle at which we're looking at, I can see all colors of the rainbow, essentially.
Yes, you see, this is essentially what is called iridescent, that the color change in function of the angle that you are observing it. And it's a characteristic of what they are called the structural color, yes? Then, for example, we made it on this really large roll and deposited on large scale, and then it's simply grinded. And then what you get is something that really is like a...
It looks like glitter for...
Yeah, it looks like glitter. So depending on the size, the bigger size, they are like really glittery.
Okay, so that's sort of sparkly green and blue
powder,
inside
yes.
this liquid.
Yes.
But I can see some bits of glass with a glittery substance on it. Some are red.
This is essentially is the same of what you see here in the vial, but they spray deposited on a substrate.
It looks beautiful. It looks like a sky full of stars of different colors.
Yeah, and then here, this is multicolored, but this one are also single color, right? So you see that they are green, all green. And then you can change the color by changing some of the characteristic of the suspension. For example, adding salt, you can tune the color. The other things, you can tune the size of this particle when you grind it, and then you have different type of effect, something that looks more homogeneous or something looks like more glitter.
So what is the biggest advantage of using cellulose instead of currently used materials for pigments?
The main advantage is that you start with something that is the most abundant polymer that you have available on the planet, and the fact that it's biocompatible, edible, and when you disperse it in the environment, it has a really low toxicity or non-toxicity to different species. So it's the convenience is just trying to have more sustainable components.
That was Silvia Vignolini. Jacopo, you just sent me a photo of some of those cellulose glitters you were looking at. They are so shiny. I would never expect you'd get something that looks so metallic out of wood.
I know, right? Even when I saw them in person, honestly, I almost thought they had faked it.
Amazing. Well, it sounds like we can now build our flats from wood. We can paint the walls with shiny, glittery colours with wood, if that's your taste. All we need now are wooden windows and wooden cutlery, which all sounds a bit far-fetched, but these have already been invented. Joining us now is Teng Li, a mechanical engineer from the University of Maryland. So Teng, transparent wood, that's a bit of an oxymoron, isn't it?
Well, yeah.
So how do you make wood transparent?
It actually has two steps over there. The first step is more chemical processing. You bleach the wood, and then the wood is penetrated with the synthetic polymer. The resulting piece of wood is actually virtually transparent.
Amazing. And why do you want to make wood transparent? What's wrong with glass?
Glass, we have been using that for many, many years in Windows and many other applications. But glass has several disadvantages indeed. For example, we know that glass is very brittle. It can be easily shattered into sharp pieces. By contrast, the transparent wood is much tougher than glass. And also the glass production in construction comes with a heavy carbon footprint. By contrast, transparent wood is made from a sustainable and renewable resource with low carbon emissions and also have a better thermal efficiency.
So even with all of that bleaching and the resins you need to add, it's still better for the environment than glass?
Hopefully, I think it has a very good potential in the future as a potential replacement for glass.
And you say a potential in the future. How big are the pieces that we've got already? Is anyone making windows out of transparent wood yet?
Not yet. So far, I believe this has been done in the lab scale, but the process I mentioned can be scalable to industrial scale when it's getting to the commercialization.
It's incredible. I can't wait to see it. Now, I hear in your lab, Teng, you have made a steak knife out of wood. What on earth gave you that idea?
Yeah, we have been working on exploring the new usage of the wood. We have this process to make the wood 23 times hotter than the natural wood. Then we were scratching our head to find a potential application of this. And we realized that actually we use hard materials a lot in our daily life. For example, dinner table knives, typically we use the stainless steel one, and at parties we use the plastic ones. And then we were trying to make a super hard wood knife. It turns out that it's actually quite sharp. It's actually sharper than the typical dinner table knives we use. We also
Wait, a wooden knife is sharper than a steel knife?
Yeah, we measured the cutting force of the super hard wood knife and compared it with the cutting force of a typical dinner table knives made of stainless steel or natural wood or plastic ones. It turns out that the super hard wood knife has a smaller cutting force.
I would never have believed that. What do you have to do to the wood to make it so hard?
It involves two steps. In the first step, it's a chemical processing. As you mentioned in the earlier of today's program, we partially remove one of the component in wood, which is the lignin. And in the second step, you can really densify the wood into a piece of material which is much harder than the natural wood.
And when you've got your wooden knife, can you still stick it in the dishwasher?
Oh, yeah. Indeed, if you look around our kitchen, we have been using wood utensils, cutting board, spoons, chopsticks, and can be used multiple times. You can wash it in dishwasher. It survived the usage for over a long time. And the durability of the super hard wood is actually better than the natural wood. So we expect that this can be used for even longer time.
Amazing. I'm one of those people who buys cheap knives and they go blunt immediately. So sounds like your wood one might actually be better. And then you've also been working on super strong wood. Can you tell me a bit more about that?
Yeah, so using the process, you can make the natural wood more than 10 times stronger than the original material. And also the resulting super strong wood is much lighter-weighted. So for example, the strength of that super strong wood is comparable or even higher than some of the steels, but the density is 6 times lighter, which means that you are getting a piece of material which is comparable to steel, but it's much lighter weighted. So it actually leads to a lot of potential as a replacement for steel.
Thank you, Teng. That's Teng Li, wrapping up our look at the construction world's material of the moment, wood. And now let's end with our question of the week. Katie King has been in the flying seat finding out the answer to this space question from Matt.
Early commercial flights were scheduled and had air traffic control, but pilots were allowed a fair amount of latitude in the early days, which resulted in some mid-air collisions. I was wondering, with 3 space missions currently converging on Mars, how do the nations involved avoid orbital collisions? Do they share data? Do they have transponders or space traffic control? Thank you.
Matt, I spoke with Chris Bridges, academic at Surrey Space Centre in the University of Surrey, to find out more about your question. Let's see if you were right. Do they share data? Do they have transponders? Or perhaps even space traffic control? Let's find out more.
So fortunately, there are not many missions out of Mars. Only about 8 or so missions are currently orbiting the planet. And if we compare that with the 34,000 objects around Earth, Mars orbits are practically empty. Each mission does indeed share data on position and speed, and we call those the state vectors of a given satellite. And this data is shared between all major agencies like NASA, ESA, plus our own UK Space Agency.
You were bang on the money, Matt. Congratulations. Nations do share data. But how is this data obtained?
For almost all missions, we use something called the Deep Space Network, and that uses a transponder to take highly accurate radio measurements to determine what we call the range and velocity.
Right again, Matt. They do also use transponders, much like aircraft send their position to air traffic control. Before answering your final question, though, I want to know, how do we determine the position and speed of a spacecraft when it's so far away?
The actual thing that we're measuring is signal lag and the Doppler shift, which gives us then a change in frequency, and we use these to determine the distance and the speed around a spacecraft at Mars.
Much like when sirens whiz past you on the street and they start to sound different due to the Doppler effect, we can use the frequency of the radio signals to determine how fast these spacecraft are going. Okay, Matt, the final question. Can you get the hat trick? Is there a dedicated space traffic control?
We don't have big space networks. We rely on a combination, really, of special messages and, critically, that operators actually share their information, like GPS data. So we have to work together that our spacecraft aren't on track for any collisions, and especially in low Earth orbit, we use thrusters to manoeuvre away if we needed to, and we often budget for this in our missions.
So, Matt, I'm afraid you didn't quite get the hat trick, as there isn't yet a dedicated space traffic control team. But as the use of space is growing so rapidly, maybe it won't be long before one exists. Thank you to Chris Bridges for your answers, and next week we will be answering Sarah's question of...
Why do ant bites hurt so much?
If you're itching to tell us your answer, you can join the debate on our forum, nakedscientists.com/forum, or email chris@thenakedscientists.com. That's it for this week. Thank you to Jacopo Russo for helping to put the show together. And next week, we are revisiting plastic. David Attenborough helped us recognise plastics as a pollution problem for the oceans, but we will be examining how plastics intersect with climate change. In what ways do they contribute to our greenhouse gas problem, and how might they be helpful in addressing it? Tune in next week to find out more. Our findings might surprise you. The Naked Scientists comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Sally LePage. Thank you for listening, and until next time, goodbye.